friends. So now we are having the continuation of a laminar flow between the two parallel stationary plates. So if you recall the earlier part of uh, this derivation, we have here uh, the two parallel fixed stationary plates are shown here, for which the four equations to be determined: the shear stress distribution, velocity distribution, and we have to find the ratio of maximum velocity to average velocity and the difference in pressure head over a given length of the two parallel plates. So we have already arrived at velocity equation, so which is shown that it is varying with the square of y, so it is equation of parabola. So this is my velocity distribution. So maximum velocity at the center of the two plates, and the velocity is having a zero values, so increasing from 0 and taking the maximum value at the center of the two plates, and decreasing back, and gaining zero velocity at the other plate. Now this is my shear stress distribution. My shear stress is 0 here. So that is exactly at the center of these two plates, and my shear stress takes the maximum value exactly at the two walls of these two plates, because more resistance against the flow, so more shear stress on the two walls of these two plates. Now we are finding out the ratio of maximum velocity to average velocity. So it is already said that velocity is maximum when y is equal to t by 2. So that is uh, we have maximum velocity exactly at the center of the two plates. So u max is equal to, so we have minus 1 by 2 mu of del p by del x into so if you take this velocity equation, so we are substituting y as t by 2. So y as t by 2 in the velocity equation. So here are also substituting y as t by 2. So we have t by 2 whole square. So we are getting the equation as, on simplifying, as 1 minus of 1 by 8 mu of del p by del x into t square. Sorry. Now the discharge Q is obtained by considering the rate of flow of the fluid through a strip of thickness dy and integrating. As we have already seen in the case of laminar flow in a circular pipe, so there also one elementary ring of radius small r is taken, taking the discharge through the elementary ring and integrating that expression to get the discharge in the entire pipe. So here also we are taking one strip of thickness dy and taking the discharge equation. So dq is equal to, okay, taking the discharge equation as area into velocity. So area of the strip into velocity at a distance y. So we have the velocity equation at a distance y earlier. So and the area of the strip we are taking it as dy into 1. So the thickness of the strip in vertical direction is taken as dy, and in the third dimension, so that is taking 1 unit length. So area of the strip is now having the height dy and the unit length, so that is 1. So area of the strip is now dy into 1. So q is now integration of dq with the integration limit 0 to t. So simplifying, we are getting our discharge equation here. Now we know the average velocity is the ratio of q by a. So q is equal to area into velocity. So velocity is equal to discharge by area. So discharge equation we got just now, substituting here area. So now we are taking the area for of both the entire two plates. So the distance between the two plates is t. So we are taking the flow through the both the plates, stationary plates, which are parallel to each other. Now area under consideration now is t into 1. So that is, if you refer the sketch, so here we are taking the flow through these two plates. So this is now the flow taking place between these two plates. So this distance is t now, and this direction. So the pipe is running for the two plates are running for a length of 1 unit length. So that's why we are taking the area as t into 1. So t into 1. So dividing maximum velocity by the average velocity. We have the maximum velocity equation what we got earlier. So that is this equation, maximum velocity equation. So taking that, now substituting average velocity is also, so everything gets cancelled here except this 12 goes up and 8 comes down. So 12 by 8. So 12 by 8 is nothing but 1.5. So it is proved that ratio of maximum velocity to average velocity is 1.5 here. Thank you.